Okay, so in this next chapter, we're going to deal with a certain class of reactions. That reaction type is going to be things that occur in aqueous solutions. So the entirety of chapter 4 deals with all of these various types of reactions. Again, they're all occurring in aqueous solutions, okay? All right, so before we start, we need to go back and remember what a solution was. Okay, so a solution, if we go back to chapter 1, was defined as a homogeneous mixture of two or more pure substances, okay? And with respect to solutions, we can vary the amounts of the pure substances that we put in. This is how we define the difference between a mixture as opposed to a compound. So with respect to solutions, all of these things are going to be in a liquid form, and there are two components to a solution. There's what we call the solvent, which is going to be the thing that is present in greatest abundance. So this is what we call the major component of a solution. And there are also going to be what is called the solute. Okay, so this is going to be the minor component, and there can be more than one solute. Okay, so solvent is a major component of a solution, whereas the solute is the minor component. All right, so specifically what we're interested in this chapter are reactions that occur in aqueous solutions. So what is an aqueous solution? Well, that is going to be a solution where the solvent is water. Okay, so aqueous solutions, we have always the solvent is water, H2O. So all of these reactions that we're going to talk about this chapter are occurring in water, okay? Okay, so let's consider a little bit more about the actual making of a solution, okay? So remember, there are two different components to a solution that we just mentioned. We have the solvent and we have the solute, okay? So both of these guys go in to make our solution. So let's say that we're making a nice solution, a nice aqueous solution, where our solvent is in our little beaker, and our solvent here is water, since this is an aqueous solution, okay? Got our little H2O floating around, and into our aqueous solution, we're going to add our solute. And our solute, let's say for this example, is something like NaCl. And when we put this in, just like you do at home, we put this in as a solid form. Right? So NaCl comes in a solid, we put it into our water, we mix it really hard, and what appears to happen to the solid, right? So we put the solid in, we mix, it appears like the solid just goes away, but we know that's not true, right? Because when we drink the resulting solution, right, it still tastes salty. It doesn't just taste like water, right? So what this is called, this essentially going away of the solid, we call this dissolving or dissolution. Okay, so there's a lot of different components that go into having these various solids or these various solutes dissolve into our solvents. Okay, so two of the important ones to consider are what we call solute-solute interactions and then solvent-solute interactions, right? So in our little example over here, our solute-solute interactions were the attractive forces that occurred between the sodium ions in our salt and the chloride ions in our salt, right? This is what we would refer to as our solute-solute interactions. So those guys are attracted to one another, right? Because remember, with these guys, we have an ionic compound. This has our charged particles, our cations, and our anions. So this is an attractive force here, right? The other thing that we have to consider is the solvent-solute interactions, right? And our solvent here, again, was just water. And we'll draw water like this, okay? So we're going to talk a little bit more in detail about this specific interaction, the solvent-solute interaction, right? Because as opposed to this ionic compound up here, we have water down here, which is a covalent compound, right? So these bonds are supposed to be the sharing of electrons, right? Not the actual, actual transfer of electrons, which is what we got to make our ionic compound. So if we're going to have any type of interaction between solvent and solute, and it's going to be electrostatic in nature, we're going to have to explain that in a little more detail, okay? Okay, so let's talk about water, our little solvent and why we would maybe see any type of interaction between solvent here and solute, Na and Cl minus, Na plus and Cl minus. Why would there be any type of attractive force between water and these two guys, okay? So again, if we redraw water, water has our little oxygen and it's got our hydrogens. And we've already said water is a covalent compound, right? Why do I know water is a covalent compound? Because this is two or more nonmetals, okay? And so in a covalent compound, in theory, the electrons that are in this bond, in these various bonds, are supposed to be shared equally, right? But that's kind of been an oversimplification, okay? If we look at oxygen, oxygen tends to be on the upper right-hand side of the periodic table, right? And so oxygen, if it were going to make any type of charged particle, tends to like to take electrons, right? If it was going to make some sort of ion, it would be a 2 minus, meaning that it has picked up 2 electrons, right? Whereas hydrogen is on the upper left-hand side, right? Hydrogen, if it was going to make an ion, tends to lose electrons instead, right? And so we see hydrogen, especially with respect to acids, as this +1, okay? So even though this is still a covalent compound, oxygen's tendency to take electrons, coupled with hydrogen's tendency to lose it, is going to manifest itself in these bonds that actually form between oxygen and hydrogen. So oxygen is going to take an unequal share of these electrons that are in this bond, okay? So even though we say, oh, covalent bonds, electrons are shared equally, in reality, oxygen's taking more than its fair share. And so what happens as a result of that is that we get what is called a partial charge formation, okay? So instead of a full charge, we're going to get a partial charge, and we denote that via this little Greek letter delta, right? So oxygen takes more than its fair share of electrons. It gets this partial negative charge. So that is what this guy is supposed to be showing, our partial negative charge. And then hydrogen, on the other hand, loses its electrons, so it develops what is called a partial positive and a partial positive, okay? So this is the electrostatic basis for why there would ever be any type of water interaction with both cations and anions, okay? Okay, so look at what actually happens when we put our sodium chloride in water. Why does it dissolve, okay? So again, we had these attractions between our solute and our solute, right? So we had our positive sodium, our negative chlorine, and these guys were attracted to one another. So in terms of what's happening with respect to dissolving, if these guys are super attracted to one another, then they're going to stay together, right? And meaning that they're going to stay as solid when we put them in water, okay? So this is an attractive force. It's going to keep them together, keep them solid, whereas we have our water and our solvent-solute interactions, right? We had our partial negative on the oxygen, partial positives on the water, and these guys are going to come in, and the partial negative of the oxygen is going to be attracted to the positive charge cation of sodium, and the partial positives of the hydrogen in our water molecule are going to be attracted to the negatively charged chlorine ion, the anion, okay? And so this is kind of like the battle that's occurring, right? Why do things dissolve? Well, if these attractive forces between our solvent-solute are greater than the attractive forces between the solute-solute, then we will see our little water molecules get in, surround these guys, and essentially lead to the dissolving of our solid compounds in solution. Okay, so how does that really look like? Big, large molecular scale. So let's imagine that we have our sodium chloride in here, right? So we've got, what's a good way to draw this? We have our sodium chloride, our big combined solid molecule, and we've got our little oxygens, right? Our little partial negative oxygens coming in and doing what is called solvating, like completely surrounding these various ions that they're essentially interacting with, right? So when we solvate with respect to our solvent, again, we are surrounding it so that we can dissolve it. When that solvation is particularly dealing with water, this is actually called hydration. Okay, so we have our little water molecules getting in near the positively charged sodiums. They're surrounding the sodiums with the negative charge oxygens, and so it completely surrounds it. Again, this is called solvating or hydration. And then on the other hand, we have our other water molecules, or the same water molecule, it's essentially, with its partially positive hydrogens, right, getting in and surrounding the chloride ions, right? So these guys come in, the water surrounds them, and then the water essentially just takes them out via the process of diffusion. Okay, so in that process, as these water molecules surround and then slowly move away from the solid, note that we are forming a positive ion and negative ion. We are forming what is called a freely moving charged particle. Okay, so what's the big deal behind that? These freely moving charged particles. So what is the definition of electricity? So electricity, if you're a pure physicist or whatever, has to do with the movement of electrons, right? Or more importantly, just the movement of charge. Right? So when we have our nice ionic compound like sodium chloride, it comes in, it dissolves in water, the water surrounds it, it hydrates it, and it moves it out and diffuses out into solution. This forms freely moving charged particles. Most importantly, this forms a solution that is able to conduct electricity. Okay, and that is kind of a hallmark of ionic compounds when they dissolve in water, when they are solvated or hydrated by water. Okay, these form solutions that are capable of conducting electricity. Okay, so any type of materials that when you take them and dissolve them in a solution and produce a solution that's able to conduct electricity, these are all called electrolytes. So you probably have heard of electrolytes before from your Gatorade. When they talk about electrolytes in Gatorade, they're talking about things like sodium ions and potassium ions. And again, these guys are coming from materials, or salts, more importantly, that fully dissolve in water, right? So when they fully dissolve in water, that's what gives them this ability to conduct electricity. So this process, this dissolving of various ionic compounds, or salts is another word for this, in water, is a process called dissociation. Okay, so when we take sodium chloride in a Cl and we put it in water, it dissociates. This is what this process is called, into sodium ions, sodium +1, and chloride ions, sodium -1. So this process is called dissociation. Okay, and so there are two different types of ionic compounds, depending on whether or not they form a very strongly conductive solution or a very weakly conductive solution, right? So the first type is what we call a strong electrolyte. So strong electrolytes, when you put them into water, completely dissociate, right? So fully dissociate, meaning that everything essentially breaks up into what we call these component ions. So you get this great solution that has all these ions moving, conducts electricity really well. And then there are other types of solids or other types of ionic compounds that are called weak electrolytes. And so in weak electrolytes, what's going to happen is that you put some sort of weak electrolytes, let's say something like AgCl. AgCl, when you put this in water, it doesn't actually dissolve very much, right? So there's very little formation of these ions, right? So very few of these actually form. And so because of that, because we don't get very many of these guys, then we get a solution that only weakly conducts electricity because there aren't a lot of these little freely moving charged particles. So again, these guys are things that are called weak electrolytes because, again, they don't dissociate very much when you put them in water, and they are only able to weakly conduct electricity because of that. Okay, so now That was ionic compounds, right? So ionic compounds, when you put them in water, dissociate into their component ions. That was that whole process of water coming in and surrounding the sodiums and the chlorines, etc. That is dissociation. So now let's consider what happens when we take a different type of solution or take a different type of compound and try to dissolve it in water. So let's consider something like sucrose, right? So sucrose is given by the chemical formula C12H22O11, right? And so we're comparing this guy, our sucrose, compared to what we just looked at, something like sodium chloride. What happens when we take sucrose and we dissolve it in water, okay? So notice that sucrose is a covalent compound. This is a molecular compound, right? So molecular compounds don't have any type of ion formation. I know it's molecular because these guys are all non-metals, right? And so this is going to behave very differently, right? Molecular compounds share electrons. They don't form ions, right? As opposed to what we were looking at before with our ionic compounds. Okay, so how is this going to be different and how is it going to be similar?
Fine, thank you. Came to me?
Yeah.
Okay.
Do you have time?
Yeah, I go to the office.
Oh, okay.
Not to the office, wherever conference room.
Okay.
So when we take our sucrose molecule, which is given by this big gigantic thing here, we're going to see a similar type of situation where certain parts of our water molecule, our negatives and our positives, are going to surround the sucrose molecule, right? But now what's really important to note is that sucrose does not break into different pieces, right? So sodium chloride did, because it was ionic and it formed these ions, Na plus and Cl minus. Sucrose, though, has all of these covalent bonds. Covalent bonds, when you put them in water, do not break, okay? So because of that, the sucrose molecule, when it dissolves, it just gets surrounded by little water molecules and just floats out into solution. But note that there are no charges that are formed, right? Because sucrose just stays as its own little molecular compound, okay? So because there are no charges when we dissolve this in water, then that means that we form a solution that is not able to conduct electricity. So we form not able to conduct electricity. And my writing, electricity. Okay, so again, sucrose dissolves in water, but it doesn't break into any ions, so we get no charge formation. It stays as this little molecular form, and so we form a solution that is not able to conduct electricity. Okay, so because of that, sucrose and other types of covalent compounds are what are called non-electrolytes, meaning that it's not weakly electrolytic at all. Instead, it just doesn't conduct electricity whatsoever. Okay, so non-electrolytes, no charge formation. We just have these individual molecules floating around in solution. Okay, so the only exception to this with respect to these molecular compounds are acids, right? So remember that acids are molecular compounds. So for example, we had something like HCl, and this was in the gas phase. Then we know, well, this is a molecular compound. Its name is hydrogen monochloride, and it's not an acid, right? So this is, again, a molecular compound in the gas phase. Now, acids, on the other hand, change whenever we put them in water, right? So we had HCl, aqueous, meaning that it's dissolved in water. Then it didn't behave like a molecular compound. Instead, it was an acid, and it behaved as if it were ionic. So the H's would form little +1 ions, and the chlorides would form -1 ions, okay? So acids are this kind of exception. They are molecular compounds, right? But the minute you put them in water, they behave as if they were ionic compounds. So this process, where we'd have an acid and we break it apart into its little component ions, as opposed to dissociation, we call this ionization. It has its own little special word, and there's a reason for that we'll get into eventually, okay? All right, so ionic compounds form electrolytic solutions. Molecular compounds do not. The only exception to that are acids, which are molecular compounds that behave like ionic compounds when we put them in water, okay? So with respect to acids, there are two different types. There are acids that we call strong acids, and the big idea behind strong acids is that they completely dissociate when we put them, or completely ionize, when we put them in water. So a strong acid is something like HCl. When you put HCl in water, all of it forms H plus ions and Cl minus ions. So we do get these ion formations. On the other hand, we also have something called weak acids, and weak acids only partially ionize when we put them in water. So that would be something like acetic acid right here. So for the most part, with acetic acid, these guys stay together, and you only get very few formation, or very little formation, of this H plus in the acetate. Okay, so then one more thing that we have to consider. So if we go back to our little acetic acid, we said that this was a weak acid, right? So weak acids, and this is the weak acid. Acetic acid is the acid of the acetate ion, right? So we have acetic acid. When it goes into water, it forms H plus, and it forms this guy, which ideally you can recognize as the polyatomic ion acetate, okay? So in general, if you'll note that when we put acetic acid in water, it broke apart again into H plus, but then this guy, our polyatomic ion acetate, it stayed together, right? And it stayed together as this little polyatomic ion, so overall it had this 1- charge. That's what's going to happen with respect to polyatomic ions when we put them in water. So other polyatomic ions, things like nitrate or something like sulfate, when they go in as some sort of solid salt or acid, so let's say HNO3, when this guy breaks apart into its different ions, it's going to break apart into H+, but then it's also going to break apart into the polyatomic ions, right? So polyatomic ions do not break up in water. They stay together. And there's a reason why, right? And this goes back to what we were just talking about. What type of bonds actually make up these polyatomic ions, right? So these are all made up of covalent bonds, like we looked at with our sucrose molecule. When we put covalent bonds in water, they do not break. Okay, so anytime you put a polyatomic ion in water, it stays together as its polyatomic ion. You don't break this up into sodium or into nitrogen plus oxygen. That's bad. Don't do that, okay? Okay, so then as an overview, what we've just covered, there are 2 or 3 different types of materials, right? So the first type of material is what is called a non-electrolyte. So this comes from molecular compounds, molecular covalent compounds, things like sucrose. So when you dissolve these guys into aqueous solutions, you get a solution that is not capable of conducting electricity at all. So you notice there is no light at the light bulb. So we call these non-electrolytes. On the other hand, if you have a solution that's only weakly conductive, right, so you get just a little bit of light shining through on this light bulb, this is because solutions are formed that are only weakly electrolytic. This is going to form from not very soluble ionic compounds, as well as weak acids, like acetic acid. And then the last type of material are strong electrolytes. Strong electrolytes are ionic compounds that dissolve really well, right? So very soluble ionic compounds, as well as very strong acids. So molecular compounds, non-electrolytes, slightly soluble ionic compounds, as well as weak acids, form weak electrolyte solutions, and then strongly soluble ionic compounds as well as strong acids form strong electrolytes. We get this nice shiny light bulb here. Okay, so this kind of leads us into this question. When we're dealing with ionic compounds, we're dealing with these type of solutions that could be either weakly electrolytic or strongly electrolytic. How are we going to know whether or not a given ionic compound is going to dissolve when we put it in water, right? So for example, if we put something like silver chloride as a solid and made an aqueous solution with that, when you put it in, it would essentially just form this nice solid silver chloride at the bottom of the beaker, right? And it would not dissolve at all. On the other hand, if you put something like silver nitrate as a solid, and you put that into water and you stirred, this would dissolve, right? So the solid would appear to go away, and you would be left with your little component ions floating around in solutions. And again, you would get a nice electrolytic solution because of that. A very nice strong electrolyte. Okay, so things that do dissolve in water, when you put them in ionic compounds that do dissolve in water, we term these soluble compounds. Okay, so they have good solubility, they're fully soluble, they dissolve when you put them in water. Whereas ionic compounds that do not dissolve in water are what we term insoluble. So when you put them in water, they just stay as their solid form. Okay, so soluble if it does dissolve, insoluble if it does not. So how are we going to know? All right, how are we going to know whether or not a particular ionic compound is soluble or insoluble? So a lot of the various things that go into being able to do this are beyond essentially the scope of this course, okay? So instead, how are you guys going to know? Well, I'm going to give you a chart that is called the solubility chart, okay? So this is how you will know whether or not a compound is soluble, it does dissolve in water, or insoluble, it does not. You're going to utilize this chart very, very, very wisely, okay? So how are you going to utilize this chart, this little solubility table, or these solubility rules? Okay, so in general, what you will find are things that are up here, all right? So things that are in this top part of this chart are generally very soluble. Soluble, okay? And so they list the various anions that you will find that are generally very soluble. And then over here, they list a couple of exceptions, right? So for example, if you had a ionic compound like sodium nitrate, right? And you were like, okay, this is my ionic compound. I'm going to put it in water. And when I do, it's going to dissociate into sodium ions as well as nitrate ions. And the question is this soluble or not? Well, the nitrate, we'll go over to our little table. We'll look for the anions. And so I've got my little nitrate ion here, and there are no exceptions, right? So if anything, any type of cation is paired with nitrate, it will always be soluble. So because of that, this is soluble, sodium nitrate, okay? On the other hand, let me get rid of yellow because that's terrible. On the other hand, what if I had something like lead bromide, okay? So again, I've got this compound. I'm like, hey, is it soluble or not? I can't tell. Will it break up into these little lead 2+ ions and bromine 1- ions? And so I take my little anion part of this and I go over to my little chart. And in my little chart, I find my little bromine. And so bromine, again, is generally soluble, except when it's paired with silver, mercury, and lead. Okay, so that's an exception. And so because of this, this is not soluble. All other compounds with bromine in them are soluble, but this guy, because it is particularly this thing with bromine or bromide, then it is not soluble, okay? So then everything down here is generally not soluble. And the exceptions, so they give you the various anions that we're dealing with. And so the exceptions over here are going to be whether or not, if it's paired with one of these exceptions, then the thing will actually be soluble. But if it is not, then these guys tend to be insoluble things, right? So for example, again, if I had something like sodium sulfide, right? So again, I'm asking, is this a soluble salt or not? I come over here, I say, oh, well, sulfide tends to be fairly insoluble, so you would think, okay, that's going to be insoluble, except right now, it is paired with sodium, right? So sodium, if I come over here for our sulfides, sulfide is insoluble, except when it's paired with something like ammonium, the alkali metal cations, and then a couple of the group 2 cations, right? So remember, sodium is an alkali metal. Sodium is an alkali metal, okay? Just a reminder, it's always group 1. Okay, so because of that, because sodium is one of these exceptions, then this guy is soluble. It will dissolve in water. Okay, so I'm going to go ahead and let you guys try this one. So I've got 3 different compounds. I want you to utilize the solubility chart and predict whether or not these guys are going to be soluble or insoluble. Okay, so give that a try. You can pause this, and then I will go over the answers after you try this. Okay, so continuing on, hopefully you've paused this, you've given these guys a try. So A, we have sodium iodide. All right, so if we go back to our little solubility chart, we would find that iodide is generally soluble. There are a couple of exceptions, but sodium is not one of them. So this is soluble. Next one is sodium carbonate. So carbonates are fairly insoluble, right? Except when they're paired with a couple of different things. Except when they're paired with alkali metals, right? So sodium again is an alkali metal, and so because of this, this is also soluble. And then the last one, again, I said carbonates are fairly insoluble. There are exceptions, but magnesium is not one of those. Okay, so because of this, we have an insoluble compound. So we have soluble, and the magnesium carbonate is insoluble. Okay, so introducing this concept of solubility is going to be important as we look at the various classes of our aqueous reactions. All right, so in general, all of the reactions that we deal with in this chapter follow the exact same formula, or exact same structure. They're all what we call double displacement reactions. So there are a couple different names for this. Some people call these exchange reactions or metathesis reactions. But essentially, what happens is you have 2 things, so 2 reactants. We'll call this A, B, and XY. And these are completely soluble compounds, okay? When you combine them in these aqueous reactions, then essentially what will happen is they will exchange their partners. So the cation from one compound will go and form a new compound with the anion from the other, and vice versa, okay? So again, this overall structure of reaction is going to be the exact same for all of the types of reactions that we look at. So this can explain the first type of reaction that we look at, which is precipitation reactions. This also is the exact same structure for acid-base reactions, as well as gas evolution reactions. So all of these guys are going to follow the same general exchange partners and get new compounds. Okay, so we're going to start by talking about precipitation reactions, and I kind of like to utilize a nice little real-life example to illustrate what a precipitation reaction is. Okay, so with respect to your sink, which is what we're going to be talking about here, so hopefully you guys know what hard water is. So hard water is water that contains a lot of dissolved magnesium as well as calcium cations, right? So the problem with hard water is that when you have these magnesium and calcium cations floating around, they tend to do various reactions with the soap that you use in both your bathtub as well as your dishwashing soap, etc. And what happens is they do these reactions and they form this gray curd, right? And this is going to line your bathtub, it's going to line your sink, etc. So that's not good. We don't like hard water because of that. So if this happens in our bathtubs, if it happens in our sinks, then you would think, well, the exact same thing is going to happen when we wash our clothes, right? If we're utilizing hard water and we put detergent or soap into our into our clothes washing machine, then you would think, oh, this gray curd is going to form on our clothes. That would be very bad, right? You get all over your clothes. It's like, well, what's the point of washing your clothes? So detergent manufacturers know about this. So they know that hard water forms this gray stuff whenever it reacts with soap. And what they do is they add compounds like sodium carbonate to their detergent, right? Well, what's that going to do exactly? So if we think about sodium carbonate, and if we go back to our little solubility table, we'll find that sodium carbonate is completely soluble. So if they add solid sodium carbonate into their detergent, right, and it goes into water, it's going to completely dissolve into its component ions. So it's going to dissolve and dissociate to form sodium +1 ions, as well as carbonate 2- ions, okay? So now you've added your detergent, you've added the water in your washing machine. The sodium carbonate is going to completely dissolve, and now you've got all of these little carbonate ions floating around in the solution, right? So it's important to note here that if we go to the solubility table, magnesium carbonate, so magnesium carbonate, as well as calcium carbonate are not soluble, right? They are insoluble, right? So all that has to happen is this little carbonate ion needs to float around. When it finds a magnesium or when it finds a calcium, it's going to have a reaction and it's going to form this solid magnesium carbonate or the solid calcium carbonate, right? So again, we're doing everything in an aqueous solution. If we form these solid compounds, what's going to happen is they are just essentially going to fall to the bottom of your washing machine, and essentially that's how these detergent manufacturers remove magnesium and calcium from our water, essentially to alleviate this hard water so that these guys don't react with the actual soap molecules and form that gray curd, okay? All right, so this is a nice little real-life illustration of a precipitation reaction. Okay, so in the precipitation reaction that we just looked at, we formed two different precipitates, magnesium carbonate and calcium carbonate. And again, what's happened is we formed a new compound that forms a solid and falls to the bottom of our reaction beaker. Okay, so overall, in general, with respect to precipitation reactions, what these guys are characterized by is taking two completely soluble solutions, right? So two completely soluble salts, mixing them together and forming something that is insoluble, right? So for example, if we took potassium iodide, completely soluble, if we looked it up on the solubility chart, as well as lead nitrate, also completely soluble, if we poured the two together, again, they're going to exchange their partners, and we're going to be left with potassium nitrate, which is soluble, right? And then also lead iodide, which is insoluble. That insoluble thing, once it forms, is going to essentially just fall to the bottom of the beaker because of the density. It's much greater than water. So we call this guy, the solid that forms at the bottom, a precipitate. Essentially, we term this as falling out of solution. So again, this is a nice little characteristic of a precipitation reaction. We get this solid formed, and the solid essentially forms this nice little packet of solid at the bottom. It falls out of the solution. All right, so not all reactions will actually form a precipitate, right? So not all reactions are precipitation reactions. For example, if we took something like potassium iodide and we combined it with sodium chloride, we would get essentially no reaction because potassium combined with calcium, so potassium, not calcium, combined with chloride, or sodium combined with iodide, these are both completely soluble aqueous compounds, right? So if you don't form a solid when you exchange the two partners, then you're not going to get any type of reaction, and you would just write, because of that, no reaction, okay? So you're only going to get a precipitate and have a precipitation reaction when one of the two products is actually insoluble. And again, you would predict that via the solubility table. So how are you going to go about actually being able to predict these precipitation reactions, okay? So I'm going to go through two or a couple of different steps on how you should go about doing this, and then I have a couple of examples for you guys to try, okay? So let's say that we had that original reaction, right, where we took potassium iodide as one of our reactants. So potassium iodide, again, this was soluble, so we denote that with the AQ, and we combined it with the lead nitrate, and again, this was completely soluble, AQ. So how would we know whether or not we got a precipitate? Okay, so there are a couple different steps involved. The first step is essentially determining what products you form. So the way I go about doing this is I take my two reactants, and I break them up into their little component ions, right? I dissociate them completely. So for potassium iodide, I've got potassium, and then I've got iodide, I minus, right? So I denote them as they're just single species, especially, and also include their charge. Then for the second one, I've got lead nitrate. So I'll write this as Pb 2 plus, because again we have a 2 plus charge, and then NO3 1 minus. Okay, so even though there's a 2 here, I'm only going to denote this as just the single ion species when it dissociates. So I write these guys as their various component ions. Then what I'm going to do is I'm going to exchange their partners. So I'm going to take potassium and I'm going to combine it with nitrate. I'm going to take iodide and I'm going to combine it with lead. Okay, and so then I predict my 2 possible products. So when I do this, I have to make sure that I am making a neutral molecule, right? So if I'm making something like K plus plus NO3 minus, when I combine these guys, I have to combine them in the ratio I need to give a neutral molecule. For this one, it ends up being K NO3, so this is one of my products. And then the other side, we have lead nitrate, so this is Pb 2 plus plus I minus. When we combine these and I get a neutral molecule, I need 2 negative ones to balance out the positive 2. So this would give me PbI2. Okay. So I take my 2 reactants, I break them up into their component ions, I switch partners, and predict my 2 possible products from that. Okay. So next, how are we going to know whether or not we get a precipitation? So now you're going to take those 2 possible products and you're going to go to the solubility table and you're going to determine the solubility of each one. Okay, so our 2 possible products here were KNO3 as well as PbI2. If we take this to the solubility table, we would find that potassium nitrate is completely soluble. So if something is soluble as a product as well as a reactant, we're always going to put the physical state of AQ. But when we look up this lead iodide, we'll find that lead iodide is insoluble, generally insoluble, right? And so because of that, we'll denote this as a solid. This will form our solid precipitate and fall out of solutions. If I had gotten both of these guys as 2 completely soluble compounds, that's when I would have written no reaction. But again, for this problem, I do have one thing that forms an insoluble solid compound, this lead iodide. Okay, so then after that, I will go ahead and write everything together. So I've got my Ki aqueous plus my lead nitrate aqueous. Go ahead and write your product. So I've got KNO3. This was aqueous plus lead iodide, which is solid. And then the last thing that you need to do, hopefully you should be able to see, is you need to balance the overall reaction, right? So for this guy, I've got 2 I's. I'm going to need 2 I's over here, so I'll put a 2 in front. But then I also will need to put a 2 in front of this guy to completely balance everything, okay? Okay. All right, so I'll do this one more time to kind of give a better example. So I want to write the precipitation, or I want to determine whether or not a precipitation reaction occurs and write the molecular equation for it when I mix solutions of potassium carbonate and nickel chloride. Okay, so potassium carbonate, I'm going to go ahead and write the chemical formula of. So potassium is K plus, carbonate, let me write this guy, potassium carbonate is CO3 2 minus. So to make a neutral compound here, I'm going to need 2 of these guys to balance the 2 minus. So I've got K2CO3. Let me write that a little bit better too. So K2CO3, right? And again, this is soluble because all of the reactants in a precipitation reaction are soluble. I'm going to combine this with nickel 2 chloride. Okay, so nickel 2 tells me this is Ni2+. Chloride forms a 1- ion, So I'm combining this with an NiCl2. Again, this is soluble, okay? So first step, write your two reactants. Then you're going to break them apart into their component ions. So for this guy, I've got little potassium ions floating around. I've got carbonate ions floating around. And then for this guy, I've got nickel 2+ ions floating around, and I've got chloride ions floating around. Okay, so wrote my two reactants. I broke them apart into their various ions. And now what I'm going to do is I'm going to exchange their partners. So potassium is going to go and form a new compound with chloride. And again, I want to form a neutral molecule. So I'm going to need one of these, and one of these will give me one of my possible products, KCl. And then I'll do the exact same thing for the other two. I've got my metal, nickel, which will come first. And this guy's a 2+. I'm going to combine it with carbonate, which is a 2-. So I just need 1-to-1 nickel CO3. Okay, so now these are my two possible products. Next, to determine whether or not I have a precipitation reaction, I'm going to go to my solubility table and I'm going to look up these two guys, right? So in the solubility table, I will find that potassium chloride is completely soluble. Okay, so to denote that, we list it as AQ. Anything that is soluble is listed as aqueous. It just stays as component ions. And the nickel carbonate, when I look it up in the solubility table, I will find that it is insoluble. And so I will denote that as a solid. Okay. Okay, so we have a precipitation reaction, right? We get our insoluble nickel carbonate formed. So now to complete this, I'm going to rewrite my reactants and my products and their physical states. So I've got K2CO3 aqueous plus nickel carbonate aqueous goes to form KCl. My first possible product, aqueous plus, wait, where did I get nickel carbonate? It wasn't nickel carbonate, it was nickel chloride. Ugh. Nickel chloride, aqueous. So potassium carbonate, nickel chloride, nickel 2 chloride, potassium chloride, and then nickel carbonate. And again, this was our solid, okay? So this is my nice precipitation reaction. The only thing I have left to do is to balance it. So for this guy, I've got 2 potassiums. I'm going to put a 2 here, and then that should balance everything. So everything should be good. Okay. So go ahead and try these. I've got 2. This isn't like a soccer tip or anything. Go ahead and try to figure out if there is a reaction between sodium nitrate, lithium sulfate. If there isn't a reaction, if you don't get any type of insoluble compound, then you would just write no reaction, and then do the same thing for sodium hydroxide as well as copper 2 bromide. Okay, so if you want to go and give that a chance, I would pause this now. If not, then I'm going to go ahead and write the solutions. So for question number 1, when we take sodium nitrate, let me go ahead back to, so when we take sodium nitrate and we combine it with lithium sulfate, we don't actually get any type of insoluble compound forming, so this would be no reaction. And then when we take number 2 and we take sodium hydroxide, aqueous, and we combine it with copper 2 bromide, which would look like this, then we would get an insoluble precipitate. We would get copper hydroxide. This would be solid, and then the other product would be sodium bromide. To balance, I would need a 2 here and then a 2 here. And denote this as AQ as well. If you have any questions about these guys, make sure to come and see me or contact me via email. Okay, so a couple more things for today. We're going to talk about how we represent these various reactions. So there are a couple different ways depending on the information that we need, or the ease with which we want to look at these, okay? So everything that we've been writing so far for these precipitation reaction, we've been writing these guys as if they existed as molecules, right? So this is what we call the molecular equation. So for that potassium chloride reaction, we had written KCl as if it existed as KCl together. We had written PbNO3 as if they existed together. And then when we went to our products, we wrote the solid together as well as the potassium nitrate. Okay, so this is what is called the molecular equation. We write these guys as if they exist as molecules, right? But the problem is that we know, especially with respect to these aqueous reactions, that they don't exist together as molecules. All of these ionic compounds instead in water exist as ions, right? This exists as K plus ions floating around and Cl minus ions floating around. This exists as Pb ions floating around as well as nitrate ions floating around. So again, when we write them like this is representative of the molecular equation. On the other hand, that isn't the real situation. So if we want to actually show what's happening in solution, the actual reality of the situation, then we can write what is called the complete ionic equation, okay? So for the complete ionic equation, any type of ionic compound, any type of strong electrolyte, any type of strong acid is going to be written as they actually exist in water, which is as ions, okay? On the other hand, any type of weak electrolytes and non-electrolytes are going to be written in their molecule form. So these are going to be things that form solids, that form liquids, that form gases in these various reactions, as well as things like weak acids, etc. So for example, I had written on the previous page the molecular equation, right? So we had our KCl, our PbNO3. So this was our molecular equation. The complete ionic equation for this reaction, we would take everything that has an AQ, right? Everything that has an AQ, and we would break it apart, dissociate it into its ion form, okay? So for this guy, KCl, if we want to write the complete ionic equation for this, we're going to break it apart into its various ions, and we're also going to take into account the stoichiometry of the reaction, right? So this 2 is distributive. So for the complete ionic equation for this, we would write 2K plus aqueous plus 2Cl minus aqueous. So that's the first one. We just dissociate it into its ions, plus a Pb2 plus aqueous. And then we've got these nitrates, and that again is going to be distributive, so it goes to both of these. So this would be plus 2 NO3 minuses aqueous. Notice that I didn't write NO3 2, right, because this doesn't exist. All this really is just 2 separate NO3 guys floating around. So this is going to go to make, so now anything that exists as a solid, liquid, or gas, we're going to keep as their actual molecule form, right? So in this precipitation reactor, we made this PbCl2. In the complete ionic equation, we're going to keep that together because it does exist together, right? It's floating at the bottom of the beaker as this molecule. I guess I can't say floating. So this is PbCl2 solid, but then everything else, this aqueous thing at the end, is going to be written in its ion form. So K, 2K plus aqueous, plus, again, this is distributive, so 2 NO3 minus aqueous, okay? So that's a hassle, but this is the complete ionic equation for this reaction. So complete ionic equation. Okay, everything exists as it actually does in solution, and then you keep any type of solids, liquids, and gases in their molecule form, again, as they do in solution. Okay, so that was a hassle. Complete ionic equations are a bit of a pain to write, right? And we should note a couple things about them. right? So if we look at our complete ionic equation from the previous slide, we will note that this guy, our little potassium, is the exact same on the reactant side as it is over here on the product side, right? Same thing with nitrate. Nitrate is this NO3 over here. It is also this NO3 over here. So potassium and nitrate, these guys in this reaction don't really do anything. They don't change at all in going from the reactants to products. So we call these guys spectator ions. They are essentially just hanging around, spectating the reaction, getting in the way of what's actually really occurring, which is chlorine finding lead and making our new compound, okay? So what will happen with respect to these spectator ions is that we can frequently remove them, okay? So who are the spectator ions again? Here we've got potassium, nitrate, potassium nitrate. So these guys are spectating because they don't do anything. And what we can do is we can take them and we can get rid of them in our reaction, right? So we can just go, hey, you don't do anything, you don't do anything, you don't do anything, you don't do anything, and be left with the real meat and potatoes of these precipitation reactions. So this guy ends up just being 2Cl minus, aqueous plus Pb, 2 plus aqueous, going to make our PbCl2, which is a solid, and we're left with this nice little compact reaction, which is what is called the net ionic equation, okay? So in the net ionic equation, we have removed all of the spectator ions. So all spectators are removed, and that's what it says right above it. Okay, so the net ionic equation here is again just the 2Cl minus reacting with the Pb2 plus, going to make our new molecule, our solid lead chloride. Net ionic equation. Okay, so I'm going to start with this on Thursday. I think that's about enough for today. So again, on Thursday, we're going to come in. I've got this question 4.2, which is, which solution will form precipitate when mixed with sodium carbonate? And you get 4 different options. In the Socrative app, there's actually other questions that go along with this that incorporate that whole molecular equation, spectator ions, net ionic equation. So make sure that you do watch this before you come to class on Thursday. Okay, so we're going to continue on today talking about our reactions that occur in water, right? Our aqueous reactions, okay? So last time we talked about the first class of our aqueous reactions, which were precipitation reactions. And so just as a reminder, for all of these reactions, they're going to kind of follow these exact same format, right? We call this the double displacement reaction, or the exchange reaction, or the metathesis reaction. And so in that, we'll have some sort of reactant, say A and B, and that reactant is completely soluble in solution, and we will combine it with another reactant, which is again completely soluble in water, in aqueous solution, and when they combine, they will essentially exchange partners, right? So the A, our cation of one, will go with the anion of the other, so we will form AY, and then our anion of one will form with the cation of the other, will form XB. Okay, so this is going to be the exact same format for all of these reactions that we talk about, right? So for precipitation reactions, we had our AB, our XY combined, and one of these things formed a solid, right? And we knew that because of the solubility rules, right? Okay, so in the last 2 classes of reactions that we're going to look at that follow this exact same format, it's going to be very similar, right? But it's going to be slightly different. So the first of the last 2 classes of reactions that we will look at are called acid-base reactions, and then the second is called the gas evolution reaction, which is essentially just a special type of acid-base. But the big difference comparatively between our solubility or our precipitation reactions is that instead of forming a solid with these guys, one of our products will be a liquid, okay, or one of our products will form a gas, okay. So precipitation, exact same thing. We had an AB combining with an XY. They exchanged their two partners and formed a solid. With acid-base reactions, with gas evolution reactions, exact same format, except we're going to be forming a liquid as a product or a gas as a product. Okay, so let's go back and talk really quickly about acids, because we've been alluding to acids quite a bit, but we haven't really quite defined them exactly, right? So we talked about acids when we talked about nomenclature, all right? So how did you know if something was an acid? Well, the big telltale was the hydrogen, right? So if you had a hydrogen in front, it was usually a good indicator that you were an acid. And the big things with acids were that they were, or we could define them as, molecular compounds that behaved as if they were ionic when we put them in water. So just as a reminder, this AQ means that something has been dissolved in water, right? So these were molecular compounds, a nonmetal with another nonmetal, but they behaved as if they were ions when we dissolved them in water, and that's what was giving them this acid nomenclature, okay? So with respect to the definition, for this first semester of general chemistry, we go by the Arrhenius definition of what an acid is. And so an acid, under the Arrhenius definition, is just something that produces these H plus ions when we put it in water. Okay, so HCl is an acid because when you put it in water, it produces this H plus. On the other hand, we're going to be dealing with bases also in this class of reactions. So we're going to be dealing with acid-base reactions. Well, what is a base? So the Arrhenius definition for what a base is something that produces OH minus ions when you put it in solution. So these things tend to be metal salts, right? So ionic compounds. So these are salts or ionic compounds that specifically contain this guy, OH minus, which is hydroxide, right? So hydroxide is just a polyatomic ion. It's OH minus. And so the Arrhenius definition of a base is something that produces OH minus when you put it in water, and this tends to be from these metal salts, these metal hydroxides like sodium hydroxide, potassium hydroxide, etc. Okay, so acid produces H plus, base produces OH minus. So just a quick little note to kind of get on the same vernacular with respect to these acids. So we just said that an acid is something that when you put it in water produces this H plus ion, right? So let's consider just for a second what this H plus ion is. So hydrogen by itself as a neutral atom has one proton in its nucleus. It has no neutrons, so 99.9 something percent of the time, hydrogen just has a proton in the nucleus. And if it's neutral atom, it will have one electron to balance that one proton, right? So now if we take that's normal hydrogen, and we make this H plus ion, we still keep our one proton in the nucleus, but now, compared to this guy, this one has lost its electron, right? So H plus is a proton, it is 0 electrons, there are 0 neutrons, so essentially H plus is just a bare proton. Okay, so we will call this multiple different things because of this. So we will call this H plus, we will call this just a proton because that's all it really is. Also something to note that a bare proton is not very stable, right? So it's pretty unstable. And so because of that, whenever this little bare proton is floating around in water, it'll find a water and it will essentially form a little complex with it, which is what we call this H3O plus. So H3O plus. This also has another name. This is called the hydronium ion. So hydronium, H3O+, H+, proton, these are essentially all the exact same, or they're all a name for the exact same thing, which is what an acid produces when you put it in water. Okay? One more thing to note, some acids, kind of like sulfuric acid, if you look at it, has more than one proton to lose, right? So sulfuric acid has 2 H pluses coming from this guy to lose when you put it in water. So this is what is called a polyprotic, meaning more than one proton. Polyprotic acid, specifically sulfuric acid, H2SO4, is diprotic because it has 2 protons to lose. Okay, so 2 protons, diprotic. If it had 3 protons, we call that triprotic. But again, this is just a class of acids called polyprotic acids. All right, so now that's an acid, that's a base, those are the definitions. Let's get back to our acid-base reactions. Okay, so acid-base reactions in general are called neutralization reactions, and there's a reason for that. So if you think about an acid, acids tend to have fairly bad connotations. They're fairly caustic, they burn, it's bad, no one likes them, right? The same exact thing could be said about a base. Bases are very caustic, they burn if you touch them, they're bad to handle, okay? So why we call these acid-base reactions neutralization reactions is because in them, you will combine an acid, which again has very caustic, bad properties, with the base, which again has very bad properties associated with it, and in the process you will form nice, harmless water and some sort of salt. Okay, so neutralization reaction, why do we call it that? It's because the acid, the base, they essentially neutralize each other's bad properties and form these harmless little molecules of water and salt. So really important to note that the net ionic equation, so remember that the net ionic equation was the ionic equation with all of the spectator ions removed, will tend to be, for these acid-base reactions, H plus OH minus going to form liquid water. Okay, and we'll talk about this a little bit more. Okay, so again, we talked really briefly earlier, there are strong acids, right? And there are also weak acids. So just as a note, you don't necessarily need to know this now, but there are only 6 really strong acids. So hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric are all strong acids. Note again that sulfuric is a diprotic acid, meaning again that there are 2 protons that actually ionize whenever it undergoes this reaction. So remember that strong acids, so these guys, strong acids are strong electrolytes. So strong electrolytes are things that are very good at conducting electricity when you put them in water. There are also, though, things that are called weak acids. And so every other type of acid besides these 6 is a weak acid. And weak acids are only weakly electrolytic. So these guys are weak electrolytes. They do not conduct water, or they do not conduct electricity very well when you put them in water, okay? There are also strong bases. So strong bases are going to be very soluble metal ions or metal hydroxides, things like lithium hydroxide, sodium, all of the group 1, as well as group 2, so calcium, strontium, and barium. There's a thing to note here about the stoichiometry with respect to these types of acids and bases. So if you're dealing with a group 1 metal, or group 1 metal hydroxide, these guys, it's always going to be just a 1-to-1 ratio. But just note that if you're dealing with a group 2, so these are the alkali earth metals, there's always going to be 2 hydroxides for every 1 base molecule, right? For every 1 metal hydroxide. So just note the stoichiometry with respect to how many hydroxide ions are actually produced when you dissolve this in water. Okay, so let's actually go about trying to do one of these types of reactions, okay? So So acid-base reactions, that's what we're dealing with here. And in this problem, they tell us to write the molecular and the net ionic equation for a reaction that occurs between hydroiodic acid and barium hydroxide. Okay, so the first step in this type of problem is to correctly identify what the chemical formula is given the names of the chemicals that we've been given, right? So hydroiodic acid is a binary acid. We know that because they use this hydro prefix. So binary, again, means just two things. So it's going to be hydrogen and one other type of element. That other element is iode as the base, so we know it's iodine. So this is hydroiodic acid. Again, it's aqueous. So we'll go ahead and write AQ. And then the other thing is barium hydroxide. So hydroxide is always this polyatomic ion OH minus. And then barium, if we look on the periodic table, is a group 2 metal, right? So it's barium 2 plus. And so then to form a neutral species, so a neutral metal hydroxide, I'm going to need 2 of these guys to balance the 2 plus on the barium. So the correct chemical formula for this is Ba, and then I need 2 of these OH minuses to balance the 2 plus. And again, this is aqueous because they tell us. How else would we know? Well, we could go to our solubility chart. So solubility rules, and look up barium hydroxide, and we would find that it is soluble, meaning it will dissolve fully in water. So that's how we represent it via this AQ. All right, so I've got my 2 reactants. I've got my HI, and I've got my barium hydroxide, so BaOH2 AQ. Now I'm going to go about predicting my products, okay? So to do that, I'm going to follow the exact same format that I did for the precipitation reactions, where I'm going to take my 2 starting materials, my 2 reactants, and I'm going to break them apart into their component ions, right? So for HI, when HI is floating in water, it doesn't exist like this. Instead, it exists as an H plus ion and an iodide ion. And then barium hydroxide, completely soluble. So when it's floating around in water, it's a barium 2 plus, and then it's an OH minus. And remember, this 2 is just telling us that there are 2 of these guys, 2 OH minuses floating around. So we don't include that when we're predicting our products. All right, so now I've broken these guys apart. I'm going to exchange their partners, and I'm going to produce neutral products. So for barium iodide, I've got, again, barium 2 plus. I would need 2 of these iodides to balance that 2 plus. So I'll write that BaI2. And then we've got HOH. This is where the water comes from. So HOH is just H2O. And we'll just know, well, that's liquid, right? So water is liquid. All right, so now the question is, well, what about this guy? Right, what about the solubility of this barium iodide? How do we know if this is soluble or not? So again, you would want to go to the solubility table. So go to solubility rules. If it's soluble, right, which I think barium iodide is, then you write an AQ, right? If it's not, then you would need to denote that by writing an S. But for this one, I believe that this is completely soluble, so we will write an AQ. So then I'm just going to erase this really quick so that we can write our products. And I'll erase this because it'll be confusing. So now we have our products. We know that we've got barium iodide. It's soluble, so we'll leave it as AQ, as well as liquid water. And we'll go ahead and write that. So we've got H2O plus BaI2 AQ. Okay. The last thing that we have to do here is we have to balance. That's where all of this kind of stoichiometry comes into play. So I'm going to go ahead really quick and erase this because we're going to need to put a number in front. So I've got 2 I's over here. I'm going to need a 2 in front of this guy. And then for every 1 H and 1 OH, I'm going to get 1 water. So if I have 2 H's, 2 OH's, I need a 2 here for water to balance everything completely. All right, so that is the complete molecular equation. This guy, okay? So now let's go about predicting the net ionic equation. So I'll go ahead and do it the hard way and then hopefully simplify it and you can see the easy way. So hard way, I'm going to go through the complete ionic. So I'm going to break everything apart. So we've got 2H plus. We've got 2 I minus. We've got a barium, AQ. We've got 2 OH minuses. Now we'll go to our products. Anything that is a solid, a liquid, or a gas will stay together in its molecular form. So we get 2 H2Os. And then we've got a BA. Let me go ahead and start to scroll. As well as 2I minus AQ. Okay, so this is the complete ionic. Let's just note that really quick. And now the net ionic is going to be the ionic equation with all the spectator ions removed. And spectator ions are things that exist as reactants as well as products in the exact same form, right? So iodide doesn't do anything here. It's a reactant as well as a product. Barium doesn't do anything. It's the same as a reactant and a product. And so the thing that we are left with for the complete or the net ionic equation, just the meat and potatoes of this reaction, is 2 H pluses plus 2 OH minuses going to make 2 waters. Okay, and that's it. All right, so got the molecular equation up above. This is how we predict our products. And then the net ionic equation is down here. So nice and pretty. So just note that with respect to acid-base reactions, as long as this salt is soluble, then this will always be the net ionic equation for an acid-base reaction. Okay? Always H plus OH minus going to make liquid water, as long as this salt is soluble. If it's not, then things will change with respect to the net ionic equation. Okay, so the last class of these reactions that we talk about are what are called gas evolution reactions. So again, this is kind of like a special type of acid-base reaction. And again, a gas evolution reaction is named as you would expect it to be. So hopefully you guys actually observed this in the lab recently. But when you combine essentially 2 aqueous reactions or 2 aqueous reactants in a gas evolution reaction, what you're going to get is the production of a gas, which will essentially manifest itself as bubbles, right? So you get a bunch of bubbles in solution. So there are really only 4 different gas evolution reactions that you need to be aware of. So the first one is the production of a gas directly. Okay, so how would this occur? So when you combine an acid, something like sulfuric acid, H2SO4, with a sulfide, so this S2 minus, and again, you follow the exact same protocol that we were doing before, where you switch partners with everyone. One way to produce a gas is just the direct production of H2S, which is a gas and is also very smelly. Okay, so hydrogen sulfide would be the production of that directly, is one way that you could produce a gas. Another way that you could produce a gas in a chemical reaction is via the production of an unstable intermediate. Okay, so there are 3 different types of these that I'm going to introduce you to that you should be aware of. So the first one is if you were to combine like a carbonate or a bicarbonate. So these guys, carbonate or bicarbonate. This is bicarbonate, pardon me. Carbonate is CO3 2 minus. If you combine this guy or this guy with an acid, you would produce H2 CO3, right? This guy, carbonic acid, is very unstable and does not really exist at all. The minute it is formed, it decomposes immediately into CO2, which is our gas, and then H2O liquid. Okay, so if you're ever doing these double displacement reactions where you produce something like carbonic acid H2CO3, you should just know that, well, that doesn't really exist. This is actually what exists as a reality, right? So CO2 and H2O, these would be the 2 products as opposed to this guy, okay? All right, so it's not just carbonates and bicarbonates that undergo this. So again, I just said if you ever produce H2CO3 in our double displacement reactions, that immediately decomposes into CO2 as a gas and H2O, which is a liquid. Okay, so these are the real products of the reaction that you should put. Same thing happens if you combine a sulfite or a bisulfite with an acid. You're going to produce H2SO3, which again is unstable and immediately decomposes into SO2, which is our gas this time, as well as water, which is a liquid. And then the final one that, if you ever produce it, will decompose as well is this ammonium hydroxide. So again, this guy is completely unstable and will decompose into NH3, ammonia, which is a gas, and then liquid water. Okay, so in this next example, I'm going to try to illustrate what I mean by this. But again, these are the 3 gas evolution reactions that occur via decomposition of some stable, unstable intermediate. And then the other one is anytime you combine any type of acid, H plus, with a sulfide, one of your products should be H2S, which is the direct production of this gas. Okay, so how would you actually go about doing one of these? So they want us to write the molecular equation for this gas evolution reaction when we mix hydrobromic acid and potassium sulfite. Okay, so again, first step in any type of reaction like this is identifying the correct reactants. So hydrobromic tells us that this is HBr, and we'll write AQ, and we're combining that with potassium sulfite. So again, hopefully you guys have memorized all of your polyatomic ions. Sulfite is SO3 2 minus, and then potassium is a K plus, right? So to combine these guys for our neutral starting reactant, I'm going to need 2 Ks to balance the 2 minus of my sulfite. And this, again, is aqueous because they tell you. All right, so I'm going to take my hydrobromic acid, and I'm going to combine it, make that a little bit more, with my potassium sulfite, K2SO3. This is aqueous. So now I'm going to take these guys, I'm going to do the exact same thing that I have always done before with respect to these double displacement reactions. I'm going to break my 2 reactants down into their component ions. So I've got H and Br minus. I've got a K plus. And then remember, sulfite is a polyatomic ion. So those guys stay together, right? I'm not going to break the S and the oxygen down because sulfite's just its own little thing. It's floating around together as a unit. All right, so now, same thing. I've broken my guys down. I'm going to go ahead and exchange partners and form neutral products. So for K and Br, that is just KBr. And then for H2 and SO3, I need 2 of these guys to balance the 2-, so this is H2SO3. But then I notice, oh, wait a minute, H2SO3, that's one of those unstable intermediates that doesn't actually really exist, and instead immediately decomposes into water, which is a liquid, and then a gas, because it's a gas evolution reaction, right? So I notice that, I say, oh, this doesn't exist, this is an intermediate species. Instead, the 2 products are really H2O and SO2, okay? So I've got my KBr, and I got my H2O and my SO2. I look up the solubility of KBr, and I notice, oh, it's aqueous, so it's completely soluble. And so now I have all of my products. So I'm going to go ahead and write everything with respect to my molecular equation. So I've got K and Br, aqueous. I'm going to start running out of room, so I'm going to go ahead and erase this guy. KBr aqueous, and then I've got my H2O, my SO2, plus H2O, which is a liquid, plus SO2, which is a gas. Okay, so this would be the correct molecular equation for this reaction. The only thing I need to do still is to balance it. So I've got 2 K's here. I'm going to need to put a 2 in front of my K over here. So let me go ahead and erase my thing. I'm going to have a 2 here. So 2, 2, that looks good. Then I just need a 2 here. And for every 2 of these guys, I need 1, and I get 1 and 1. So then everything else looks good. Okay. So that is the molecular equation for gas evolution reaction. Again, with respect to these gas evolution reactions, there are only 4 of them, right? And it's just noting that this intermediate that we predict when we combine our 2 reactant, right? This intermediate doesn't exist, and instead it decomposes into water and whatever gas it's making. So for the H2SO3, that gas is SO2. If this was H2CO3 on the other hand, that gas would be CO2. Okay, so now we're going to talk about a different type of reaction. Okay, so we've gotten through our 3 different types of double displacement reactions. We've talked about precipitation, we've talked about acid-base, we've talked about gas evolution. Now we're going to move on to a different type of reaction, which are called oxidation reduction reactions. And so oxidation reduction is kind of a mouthful of words, so we will frequently abbreviate this oxidation reduction reaction and use this guy instead, which is just redox. So redox reactions, oxidation reduction reactions, these are synonymous with one another, okay? So what's the big idea behind redox reactions? Well, in redox reactions, what we're going to see is the transfer of electrons from one reactant to another, okay? So this occurs very frequently when we react something with molecular oxygen. So any type of combustion reaction that we've been looking at is technically a redox reaction. Also, the oxidation of iron in the presence of oxygen. So this essentially manifests itself as the rusting of iron. This is also a redox reaction. So lots of different types of redox reactions. So when we look at the reaction with oxygen, it's sometimes hard to see exactly how that's a redox reaction. But a nice little reaction to really illustrate what's occurring with respect to these oxidation reduction reactions is what happens when we put sodium metal in the presence of chlorine gas, right? So let's say that we have as our reactant sodium metal, and we've got chlorine gas, and they go to form this very familiar sodium chloride. So nice little solid salt, okay? So again, this is a very good example of a redox reaction. Well, how is it an example of a redox reaction? So if we take our sodium reactant, right, so we have our sodium metal, and we look up sodium in the periodic table, we will find that in this neutral metal, there are 11 protons in the nucleus, so 11 plus 1 charges, And again, as a neutral molecule, there are 11 electrons, right? The same exact number of electrons as there are protons to make our overall charge be 0, all right? So that's sodium, that's our reactant, okay? And what it goes to form as a product is over here. So sodium in this ionic compound, right? So sodium in this ionic compound is Na+, right? So for Na+, we still have our same 11 protons, right? But now, comparatively, with this plus sign, there is one less electron than there is protons. Because again, we've got a +1, that means our protons have one more than the electrons, so we have essentially only 10 electrons, okay? So to go from this guy, our sodium metal, which was neutral, to this guy, our sodium +1 cation, we would have had to have lost an electron. Okay, so sodium has lost an electron. Well, where is that electron gone? So we can go over here and look at the other reactant, chlorine. So chlorine in this little diatomic chlorine is a neutral molecule, but when it goes over to form the sodium chloride, we now have it in the form of sodium, or not sodium. Have I been saying sodium? So chlorine, neutral guy over here, neutral gas. When we go over to the products, it forms this chlorine -1 ion, like this anion. To have this -1, it had to have gained an electron, right? So it had to have gained electrons. So what has happened in this reaction? Sodium has lost an electron, and it has given it to chlorine, okay, to get our sodium +1 and our chlorine -1. So this is the perfect example of what a redox reaction is, the transfer of an electron from one reactant to another. Okay, so what we call these things, so these guys, these different processes are given names. So again, with sodium in that reaction lost an electron, so we can represent that electron as a product in this reaction, and this process of losing electrons is called oxidation. So sodium was oxidized, whereas chlorine, in that last reaction, chlorine gained electrons, right? So this gain of electrons, we represent electrons as a reactant here. This gain of electrons is what is called reduction. So I think I draw this a little bit later, but just to let you guys know now, to help memorize what oxidation and reduction is. So loss of electrons is oxidation. So Leo the lion says gain of electrons is reduction. So Leo the lion says grr, loss of electrons oxidation, gain of electrons is reduction, and then you can draw Leo over here, and Leo is saying grr, okay? So loss of electron oxidation, gain of electron is reduction. All right, so that was nice and easy with respect to sodium and chlorine because we actually formed charged molecules, right? We formed a +1 ion, a -1 ion. So it was a little bit easier to see the actual transfer of electrons, but a lot of times redox reactions will occur when there isn't any type of ion formation. So it's a little bit harder to see whether or not electrons have been transferred. So a good example of that is this reaction between hydrogen and chlorine to form HCl. And it's important to note that this is HCl as a gas, so this is not our acid. This is a molecular compound. Right? So if we look at our two reactants, we've got hydrogen. So hydrogen is over here, and in this molecule, this H molecule, the electrons here in this bond are shared equally between the two hydrogens. And if we look at the other reactant, our chlorine, we're going to see the exact same thing. So we have equal distribution of the electrons that are in the bond between the hydrogen and the bond between chlorine, right? So we've got hydrogen diatomic, chlorine diatomic, both of those two atoms, and each of those reactants are sharing the electrons equally. Now when we go to products, we will find something else entirely. So when we go to products, our product is HCl, and this is very similar to what we were seeing with water when we were talking about why water is such a good solvent, or why water ends up being a solvent for a lot of different things. So for HCl, right, we draw that as if it were a nice bond between them, a nice covalent bond. But in reality, there's unequal sharing or unequal electron distribution in this bond, right? Chlorine is on the very far right of the periodic table. It tends to like to take electrons more comparatively to hydrogen, right? So there is an unequal distribution of electrons in this bond. So that chlorine forms what we call, again, a partial negative charge, and hydrogen forms what we call a partial positive charge. So we go with molecules that had complete equal sharing of electrons, right? So hydrogen had equal sharing, chlorine had equal sharing, and we make a molecule where there is an uneven distribution of electrons in the product, where chlorine gets more than hydrogen, right? So in this situation, chlorine has, in theory, gained more electrons, and hydrogen has lost electrons, right? So chlorine has been essentially reduced here, and hydrogen has been oxidized, even though we don't actually get this production of charges, okay? So this is another good example of a redox reaction. So that's like going through like how you could look at these various reactions and say whether or not something has gained electrons, something has been reduced, or something has lost electrons, something's been oxidized. But another very helpful way for us to be able to track these types of processes is via the assignment of what is called oxidation states. Okay, so it's important to note that what we're going to talk about next, this oxidation state stuff, is a fictional type thing. Okay, so oxidation states, even though we write them as if they were charges, are not real charges. They're not like ions at all. They're instead kind of just like a bookkeeping method that allows us to keep track of electrons in a reaction and know whether or not a redox reaction has actually occurred. Okay, so I'm going to go through in the next few slides the rules of assigning oxidation states to things, and then we're going to actually apply it and demonstrate how that allows us to track electrons in a chemical reaction. Okay, so there are a bunch of different rules for how to assign oxidation states. Some of them are very easy to understand, some of them are a little bit more complex. So the first one is that anything that is in its elemental form, so it's like natural form, the way you would find it in nature, has an oxidation state that is equal to 0. Right? So if we had gone back to our sodium reaction, so our sodium reaction and our chlorine reaction, we would have assigned the oxidation state of both of these guys. So sodium's oxidation state would have been 0, chlorine's oxidation state would have been 0. And I just want to note really quickly that a lot of times I will use this OS. So this is OS, and what I'm saying here is this is just short for oxidation state. Okay, this isn't its own special thing, it's just meaning this is the oxidation state of this guy. So sodium, again, oxidation state of 0, chlorine, oxidation state of 0, because this is how we would find them in their elemental form. So chlorine is a little bit of a odd one, right? Remember that there were a couple molecules that were diatomic naturally, so hydrogen, nitrogen, oxygen, and then chlorine, bromine, and iodine have, have no fear, oh, fluorine too, pardon me, have no fear of ice cold beer. Okay, so these guys were our diatomic molecules, and all of these guys are going to be diatomic in their elemental form. Okay, everything else will essentially just be a monoatomic molecule in its elemental form. So sodium was monoatomic, just one of them, but these diatomics, these are the elemental forms of these molecules. All right, so then rule number 2, with respect to assigning oxidation states, if you have a monoatomic ion, so things like calcium 2+ or chlorine 1-, the oxidation state is just going to be the charge of the ion. So the oxidation state of calcium 2+ is a +2, of chlorine- is a -1. Okay, so if you have a monoatomic ion, the oxidation state is just going to equal the charge of the ion. That's a pretty easy one. Okay, so then rule 3, things start to get a little bit more complicated. So what rule 3 states is that if you have a molecule, okay, so you have a molecule, have more than a couple of atoms together to form a molecule, the sum of the oxidation states of all the atoms have to essentially equal the sum of the charge of the molecule. Okay, so I'll try to demonstrate what I mean by that. So for example, if we had water here, water is neutral, right? So it has a neutral charge overall. So what this states is that the sum of all of the atoms in this molecule has to equal the charge of the molecule. So we have 2 oxidation state of hydrogens plus the oxidation state of oxygen. These guys both have to sum to 0, right? So the sum of the oxidation states of the atoms in a molecule have to sum to the overall charge. For a neutral molecule, that has to be 0. If we have instead something like a polyatomic ion, then again, it would have to sum to the charge of that polyatomic ion. So for nitrate, the oxidation state of nitrogen plus 3, because there are 3 oxygens, times the oxidation state of oxygen has to sum to the charge of the molecule. For this guy, this is -1. Okay? Alright, so that's going to get confusing, but we'll make it make sense in a second. Then, if we do have these molecules, we do have these compounds, how do we know how to assign these oxidation states? We're going to follow a couple of different rules. Okay, so number 1, things that are at the top of this number 4 are going to trump everything at the bottom, right? So how do we assign oxidation states to atoms in a compound? Well, number 1, anything that is in group 1, so group 1 metals are always going to have a positive 1 oxidation state. So sodium in this compound, it's a group 1 metal, it'll always have a positive oxidation state. And then group 2 metals will come after that. Group 2 metals will always have a positive 2 oxidation state. So the magnesium in our compound here will be a +2 with respect to oxidation state. Then, next, the last one, when we're assigning the oxidation state of nonmetals, we are going to assign them in order of priority, right? So everything at the top of this list is going to get priority over everything at the bottom. Okay, so fluorine, we would assign first. It will have an oxidation state equal to -1. Hydrogen would come next. It'll have an oxidation state of +1. Oxygen is a -2. And then we go back to group 7, which has a -1. Group 6, -2. And then anything else in group 5 would have a -3. So again, all of these rules in isolation don't really necessarily make sense, but they will hopefully make sense whenever we apply them in an example. Okay, so this essentially just states or restates in a nice written form what I just said in the previous slides. Okay, so I'm going to go ahead and skip ahead to the example to illustrate how you guys are going to apply these rules for assigning oxidation states. Okay, so for example, I have a list here, 1 through 5, and I want to assign the oxidation state to each atom in the compound, if I have a compound, or ion, if I have an ion, etc. Okay, so for example, number 1, rules for assigning oxidation state. So my first one is chlorine. I want to assign the oxidation state to chlorine. So again, this is the elemental form of chlorine. And so it's going to have an oxidation state equal to 0. And this goes back to rule number 1, right? So rule number 1, anything in its elemental form has an oxidation state of 0. This is the elemental form of chlorine, so it has an oxidation state equal to 0. Okay, so that's nice. So 0 for number 1. Number 2, we've got sodium, and this is a sodium +1 ion, right? So this goes back to rule number 2, which states that if you have a monoatomic ion, The oxidation state is just the charge on the ion. So the oxidation state of sodium here is just going to be the charge of the ion, so this is just a +1. Okay, so oxidation state, anything in its elemental form is 0. Anything that is a monoatomic ion is going to have the same oxidation state as the charge on the ion. Alright, so then number 3, we're dealing with Kf. So Kf is the first time that we have a molecule or a compound, okay? And so this is going to apply rule 3 and then 4 as well as 5, right? So 3 says that when we have a compound, the oxidation states of all of the atoms in the compound have to sum to the overall charge of the compound, right? So what this tells us is that the oxidation state of potassium plus the oxidation state of fluorine has to sum to the overall charge of this compound. This guy is just a 0, right? It's a neutral molecule, so these guys have to sum to 0. Alright, so that's rule number 3, essentially. Rule number 4 tells us who we get to assign first between potassium and fluorine. And then the other thing is always just going to depend on the thing that we get to assign first, okay? So rule 4 tells us that if we have a group 1 metal, that group 1 metal is always going to have a +1 oxidation state. Potassium is a group 1 metal, right? So that's going to trump fluorine. So potassium has a +1 oxidation state. So then fluorine is going to take on whatever oxidation state it needs to make rule 3 work, right? So 1 plus this unknown is going to equal 0, so fluorine has to have an oxidation state here of a -1. Okay, so oxidation state of potassium is a +1, and then oxidation state of fluorine is a -1 in this compound. Okay, so now let's move on to CO2. So again, we have a molecule, a compound now, and this molecule is a neutral charge, neutrally charged, right? So whatever these guys are, they're going to have to sum to an overall charge equal to 0 because CO2 has a net neutral charge, so its charge is 0. Alright, so now, again, going back to rule 4, or I guess now rule 5, right here we have 2 nonmetals, right? We've got a carbon, so we're going to have an oxidation state of carbon, plus we've got 2 oxygens. We have 2 times the oxidation state of oxygen. I've run out of room here. So oxidation state of carbon plus 2 times the oxidation state of oxygen is going to equal 0, because again we have a neutral molecule. Now the question becomes, in rule 5, who do we get to assign first, right? Who took precedent on that nonmetals list? So we look at that list, we'll find fluorine, hydrogen, and then oxygen. So oxygen we will assign first for this compound. It's going to take on an oxidation state of a -2. So 2, because there are 2 oxygens, times the oxidation state of oxygen, which is -2, plus this unknown for carbon is going to equal 0. So whenever we do that, we find that the oxidation state of carbon here is a +4. So for this guy, we've got oxidation state of oxygen is equal to a -2, and we've got oxidation state of carbon equal to a +4. And again, this goes back to rule 3. We were allowed to assign oxygen first. It had a -2 oxidation state, and so carbon is going to take on whatever it needs to make sure that these guys all sum to 0. Okay, so then last one, we've got sulfate. So I'm going to take my little sulfate here. I'm going to go over here with it. So now we have a polyatomic ion, right? So again, it's a compound, just like we've done for Kf, just like we've done for CO2. But now the big difference is that this is not neutral, right? It has a charge to it. So the only thing that's going to change here again, this plus 4 of these have to sum to the charge of the overall ion. And so now everything, instead of summing to 0, is going to sum to -2 because that's the charge of our compound. So now we've got the oxidation state. We do this oxidation state of sulfur plus 4 times the oxidation state of oxygen. And again, run out of room, of oxygen is equal to a -2. So between sulfur and oxygen, when we go back to that list for Rule 5, we'll find that oxygen gets assigned first. So fluorine, hydrogen, oxygen, then we go to group 7, then we go to the rest of group 6. Sulfur is in the rest of group 6. We will assign oxygen first then, right? So now we'll have the sulfur oxidation state. We'll represent that as just some sort of unknown X, plus 4 times the oxidation state of oxygen, which in that chart gave us a -2. This is going to be equal to a -2. So we have X minus 8 is equal to a -2. So X has to be a +6, okay? So oxidation state of sulfur is a +6 here. Oxidation state of oxygen is a -2. Okay, so that's easy, right? Oxidation state, applying oxidation state rules, assigning the oxidation states of things. So I'm going to go ahead and let you guys do this one on your own. I'm going to probably put something like this on the key of being able to assign oxidation states to various atoms depending on the compounds. Okay, so make sure you guys are comfortable with that. Okay, so all of these oxidation state things kind of seem silly and boring, but there is a reason why we actually do this, and there's a reason why we utilize them. All right, so the reason why we assign oxidation states is so that we can know whether or not a redox reaction has occurred. Okay, so just as a reminder, in a redox reaction, if you lose electrons, that is considered oxidation, and if you gain electrons, that is called reduction. And just as a reminder, Leo the Lion, loss of electrons, oxidation, says gain of electrons is reduction. Okay, so things that lose electrons in a chemical reaction are going to be oxidized. Things that gain electrons in a chemical reaction are going to be reduced. And again, how does this apply to oxidation states? Well, oxidation is going to represent itself as an increase in the oxidation state of something, whereas reduction is going to represent itself as a decrease in the oxidation state of something. All right, so what do we mean by that? How are we going to apply it? Okay, so how are we going to utilize these oxidation states to determine whether or not a redox reaction has occurred? Okay, so let's imagine that we have a reaction like this, where we've got carbon and sulfur combining to form this compound, carbon disulfide. Okay, so if we went in and we assigned oxidation states to everything, so carbon is in its elemental form, it would have an oxidation state of 0. Sulfur is also in its elemental form, it would also have an oxidation state of 0. And then we would move over to our compound, this carbon disulfide, and we would note, okay, well, overall this has a charge of 0. It's a neutral compound. And in it, we've got 1 carbon. So we'll say the oxidation state of carbon, we've got 2 sulfurs, so 2 times the oxidation state of sulfur has to equal 0. Between carbon and sulfur, we'll find, okay, well, sulfur is more predictable. It's a group 6A, right? So it's right underneath oxygen. It'll have an oxidation state of 2. And so then carbon will be assigned last. So we've got 2 times a -2 gives us a 0. And so carbon has to be a +4. Okay, so then we use our oxidation states here and a -2. Okay, so now in going from 0, which is what happens to carbon, as a reactant, all the way to +4 as a product, right? So it goes from a 0 to a +4. This is an increase in oxidation state, right? So an increase in oxidation state, how can that occur? How can you have something that goes from a 0 to a positive value? Well, this guy has to lose electrons to do that, right? So to increase the oxidation state, you have to lose electrons, and so that's how you know that carbon has been oxidized in this reaction, right? It lost electrons, it was oxidized, this is oxidation, okay? Again, that manifests itself as an increase in oxidation state in going from a reactant to a product. On the other hand, we've got sulfur here. So sulfur goes from a 0 as a reactant to a -2 as a product. So for sulfur, we've gone from 0 to a -2, right? The only way to go from something that's 0 to a negative value is to gain electrons, right? So we have a decrease in oxidation state here. So this is decrease in oxidation state. We have to have gained electrons to do that. So this is reduction. And this is how we know whether or not something has been oxidized or reduced. We've got carbon, which which was losing electrons, which was oxidized, and we saw that because it went from a 0 to a +4. We saw an increase in oxidation state. Whereas for sulfur, we go from a 0 to a -2. That is a decrease in oxidation state, and so that is reduction. Okay. All right, so let's utilize that in a little bit more difficult of an example. So we have this reaction between magnesium and water to form magnesium hydroxide and hydrogen gas. So magnesium, water, magnesium hydroxide, hydrogen gas. And we're trying to determine, number one, whether or not a redox reaction has occurred. And number two, what's been oxidized, right? So identify the element that is oxidized and the element that is reduced. So both what has been oxidized and what has been reduced, okay? So to do this, what you guys have to do, you have to go through and assign oxidation states to everything in the compound, or everything in the reaction. All right, so if we start over here with magnesium, it does that. So we start over here with magnesium, right? Magnesium solid, this is the elemental form of magnesium. So we have an oxidation state here equal to 0. Okay, so then if we move over to our other reactant, we've got water, right? So water is a compound. There are 2 atoms in that compound. And again, it's going to sum to an overall neutral molecule, or a neutral compound. So we've got 2 times the oxidation state of hydrogen plus 1 times the oxidation state of oxygen is going to be equal to 0. Between hydrogen and oxygen, hydrogen is more predictable. It is higher on that list that I gave you comparatively, and it has an oxidation state of +1. So the oxidation state of oxygen is going to essentially be determined by that, right? So we've got 2 times +1 plus the oxidation state of oxygen equals 0. So the oxidation state of oxygen here has to be a -2. So we've got for hydrogen a +1 and for oxygen a -2. Okay, so then that's the reactants. But to know whether or not something is oxidized or reduced, we have to see what happens to their oxidation state in the products. Okay, so I'm going to go over to my products. I've got my first product, magnesium hydroxide. And so I'm going to go through and do the exact same thing that I've been doing, right? We've got magnesium hydroxide, so MgOH2. This overall is a neutral compound. So these guys are going to sum to 0. So we've got, let's divide this. We've got oxidation state of magnesium plus, this is distributive, so I've got 2 times the oxidation state of oxygen plus 2 times the oxidation state of hydrogen equal to 0. Between magnesium and oxygen and hydrogen, magnesium is a group 2 metal, so again, it's going to be the most predictable. That comes back to that rule 4. It's got a +2 oxidation state. And then for oxygen, We will leave that one. That's the least predictable of these three. Hydrogen comes next. It's got a +1. So oxygen is going to have an oxidation state dependent on these two, right? So right now we've got a +2 plus a 2x plus a 2 times +1 is a +2, right? So then 2x is going to be equal to -4. -4, so x is equal to -2. So that's pretty standard. We've got a +2 here, a -2, and a +1. And again, we're looking at this with respect to one single atom, right? So while the two oxygens together had a -4, we want it just for the oxidation state of one oxygen. So this is a -2 for one and a +1 for the hydrogen. And then we go to H2 gas, our last product. H2 gas, if you remember, is hydrogen in its elemental form. So elemental form. So this guy has an oxidation state equal to 0. Okay, so now everything has been given its oxidation state. So we can see that magnesium goes from a 0 to a +2. So we have an increase in oxidation state. So to go from a 0 to a +2, we have to have lost electrons. Increase in oxidation state, loss of electrons, so this is oxidation. Whereas for hydrogen here, we go from a +1 all the way to a 0 over here, right? So we have a decrease in oxidation state, right? So if we go from a +1 to a 0, the only way to do that is to lose electrons. No, Chelsea. That is not the only way to do that. The only way to do that is to gain electrons, right? So gain of electrons will make things more negative. We go from a +1 to a 0. And so this is reduction. Okay, so increase in oxidation state. So increase in oxidation state is oxidation. Decrease in oxidation state is reduction. Okay, and so here, what was oxidized? Well, magnesium. Magnesium was oxidized. And what was reduced? Hydrogen. And that's how you would utilize oxidation states to determine that. Okay, so I'll let you guys try this one on your own. Same type of thing. We've got a reaction. You're going to utilize oxidation states to determine whether or not, or who's been oxidized and who's been reduced. So this is a redox reaction. Something will change with respect to oxidation state, and it's your job to determine what that change is. So identify who's been oxidized and who's been reduced in this chemical reaction. So it's important to note, right here at the end, we're going to introduce one more little vocabulary term with respect to these redox reactions. So again, these guys can't occur by themselves, right? You can't have a reaction where something is oxidized and nothing is reduced, right? Then electrons would just kind of disappear into the ether. So that's not going to happen. So if you have something that is oxidized, you will also have something that is reduced in a chemical reaction. These guys go hand in hand. And so that gives us kind of another little vocabulary term that we have to use. So if we go back to our little reaction that we were looking at before with respect to carbon and sulfur, so remember that carbon as a reactant had an oxidation state of 0, sulfur had an oxidation of 0, and then when we went to the products, we found that carbon became +4 and sulfur, one sulfur was a -1, right? So we saw that carbon here, in increasing its oxidation state, was oxidized, it lost electrons, and sulfur was correspondingly reduced, it gained electrons, and that's why we go from 0 to a -2, because again, electrons are negatively charged, okay? So one can occur without the other. So we utilize another little idea with respect to these redox reactions to define something called the oxidizing agent and the reducing agent, okay? So carbon here was oxidized, right? It lost its electrons. But it lost its electrons because it gave them to sulfur. All right, so sulfur gained the electrons, it was reduced. I think I just keep calling this copper. Carbon, my bad, carbon lost its electrons, okay? So what's the point of this again? Carbon was oxidized, lost its electrons, and in the process, it gave them to sulfur, who was reduced. So carbon here is what we call the reducing agent. It is the thing that did the reduction, right? It gave up its electrons to sulfur, it reduced sulfur in the process, so it was the reducing agent. Whereas sulfur was reduced, right? It took electrons from somebody, so the thing that it took electrons from essentially was oxidized, okay? So because of that, sulfur here is the oxidizing agent. It is the thing that did the oxidation. It stripped electrons from carbon, and so it is the oxidizing agent. So the thing that is oxidized in a chemical reaction is defined as the reducing agent, right? So if you lose electrons, that means you gave them to somebody, so you do the reduction. Whereas the thing that is reduced in a chemical reaction, it is the oxidizing agent. You took somebody's electrons away from them, and so you oxidize them in the process, okay? So it's kind of like a little flip. The thing that's oxidized, reducing agent. The thing that is reduced is the oxidizing agent. So again, go ahead and apply this in this problem. This will probably be on the quiz that I post. So you're going to use oxidation states to determine who has been oxidized and who has been reduced. But now, using your new definitions, you're also going to determine who is the oxidizing agent, who is the reducing agent in this chemical reaction. It's important to note that with respect to redox reactions, we never look at the products with respect to anything, right? So if I'm asking for who's been oxidized, who's been reduced, who's the oxidizing agent, who's the reducing agent, you will never look at the products to determine that. It's always going to be one of our reactants, okay? So not products, only reactants. So go ahead and try that, and hopefully you'll be correct in the quiz.